Hello, good evening students. Welcome back to our physics topper classes. Today our topic is magnetic effects of current and magnetism. As we are preparing for JEE advanced, let us not waste more time, right? Let us directly go to the questions. Okay. Our first question is, you can read it. A battery is connected between 2 points A and B on the circumference of a uniform conducting ring of radius r and resistance r. So, whenever we read a question, first whenever we read one line, let us try to analyze or visualize it. So, a battery is connected between 2 points A and B on the circumference of a uniform conducting ring of radius r and resistance r. So, let this be the conducting ring of radius r and its resistance is r. One of the arcs AB of the ring subtends an angle theta at the center. So, the battery is connected between 2 points. So, let these are the 2 points A and B. So, we are connecting a battery like this, right? One of the arcs AB, let this arc, see there are two arcs, one this arc and one this arc. The arc AB of the ring subtends an angle theta at the center. Let this is the center, let the center is O, this angle is theta. The value of the magnetic induction at the center due to the current in the ring is. So, we have to answer this. Let us go to the solution. We have just briefed the solution similarly. See, this is the battery connected to these 2 points A and B, right? And this is the conducting wire. Now, when you are connecting a battery between 2 points, then what the conducting wire is behaving as two paths. This is one path of current flow. This is another path of current flow. Now, you know, whenever a current is flowing through a conducting wire, a magnetic field is generated in its vicinity. So, our question is, we have to find the value of the magnetic induction, means the magnetic field generated at the center due to the current in the ring. Okay. So, this so now this is the context of the problem. Now see, because of this battery, say I1 current is flowing through this arc and say I2 current is flowing through this arc. Now see, you know the resistance R is given as R. R is the resistance for the whole circuit of the whole conducting wire. So, definitely the resistance of the path will be dependent on the length, right? And the current that are flowing, that would depend inversely on the resistance, right? The current that are flowing, it will be definitely inversely dependent on the resistance, as the potential difference across these 2 points is the same. Now, we can say, as resistance is itself proportional to the length, then we can say the current is inversely proportional to the length. So, if it is longer length, means I2 will be lesser than I1. Now, why we are discussing on current? Because we need to find out the magnetic field generated at the center of the coil. Now, definitely the magnetic field that is generated is dependent on current. Is dependent on current. Now, how is it dependent? Okay, for any circular coil, you need to remember the formula. the magnetic field B at the center of the coil is nothing but mu 0 I by 2r, where r is the radius of the coil. Now, this is for a whole circle, right? Now, if we consider only an angle theta, that is, we are not considering the whole circular coil, we are considering only this part, we are considering only this arc which is subtending an angle of theta, then definitely this B theta will be mu 0 I by 2r into ratio of the angle theta in radian by 2 pi, right, which I can write mu 0 I theta by 4 pi r, mu 0 I theta by 4 pi r. See, it is already written in the solution, right? So, B, the magnetic field that is generated at the center of the coil, is dependent on the angle theta, mu 0 I by 4 pi r into theta. Now, see, mu 0, 4 pi r, all these things are constant, like r is a radius, it is constant. So, this B is proportional to then I into theta. So, the magnetic field that will be generated at the center will be proportional to the multiplication or the product of I into theta. So, now we need to find out what are the dependence of I and theta. Let us come back to our dependence. So, we have seen that I is inversely proportional to the resistance. So, I is inversely proportional to the length. Now, each length is also directly proportional to the angle theta. So, I can write I is inversely proportional to the angle theta. Why? This is the length is proportional to the angle theta. If we can write the arc length L is nothing but r into theta, right, and r is constant. So, instead of L, we can write the current I is inversely proportional to the angle theta. So, if it is inversely proportional to the angle theta, then it definitely means that the current I into theta, the product of current I into the angle is nothing but a constant. So, what we see, the magnetic field is proportional to I theta. Now, I theta is constant. So, magnetic field is also constant, means the magnetic field generated by any arc length will be equal at the center, So, the magnetic field generated by the longer arc length AB, right, is equal to magnetic field generated by the smaller arc length, this ACB. One is ADB, so I can write B magnetic field by ADB is equals to magnetic field B ACB. Now, we have to note what direction this magnetic field is working. Now, see, when a current, like corkscrew rule or right hand thumb rule, if current is going like this, I am curling my hand, the magnetic field by ADB is in this direction, that is inside the board. And if I curl my hand like this, for ACB, the magnetic field is outside the board. They are equal and opposite in direction. So, if it is equal and opposite in direction, then what will be the net magnetic field? It is 0. They will cancel out. So, let us get back to the options. So, it will proportional no, inverse proportional no. It will be 0 only if theta is 180. No, this is also not the option. It's only 0 for all values of theta. Understand? So, the answer will be 0 for all values of theta. So, in brief, what we did, we tried to find out what is the dependence of magnetic field with current I and theta. And then we also have seen how current is dependent or whether it is actually dependent on angle theta or not. And then we have combined the concept to get that magnetic field is 0 at the center. Let us go to the second problem. Okay. Our second problem is a long insulated copper wire is closely wound as a spiral of n turns. This is a spiral of n turns. The spiral has inner radius A, you can see that, inner radius A and an outer radius B. So, this is the outer radius, this is B and this is A. The spiral lies in the xy plane and a steady current I flows through the wire. The Z component of the magnetic field at the center we have to find out. Now, there are two things to observe. One is, as it is spiraling, so means it is nearly circular in shape. So, we can use the formula of a circular coil, but as a radius is slowly increasing, right, the number of turns, as there are number of turns per unit radii, it is also varying. So, the formula for the circular ring to get magnetic field will also be changing. Let us see how we can do that. Let us consider, if you remember, see here in the spiral, one radius, the smallest radius is A, the larger radius is B, right? The number of turns is capital N. The number of turns is capital N. So, what is number of turns per unit length? Per unit length means basically per unit radii. See, the number of turns is varying between A and B. So, number of turns per unit length will be nothing but capital N divided by B minus A, right? Let us move on. Let us consider this is one portion of the spiral ring, right, the spiral coil. In this, let us consider this area. We are considering one small area of turns whose radii is dr, whose radii is r, and this thickness is dr. Now, we have got that number of turns per unit length is B minus A. Let us consider for this dr thickness, for this dr thickness, you can see this gray area, the number of turns is, say it is dn. So, dn will be nothing but in B minus A, that is number of turns per unit length, into the length is, the varying length is nothing but dr, right. Now, see, and we are considering this to be a circular circular coil having number of turns. So, as we have used in our previous problem, B for a circular coil is nothing but mu 0 Ni by 2r. In our previous problem, if you remember, number of turns was 1. So, we have taken mu I by 2r. But in this problem, as we are taking number of turns, so it is mu 0 Ni 2r, right? And this is the general formula. Now, for a small b it will be, it is dB. So, mu 0, instead of n, we are writing dn, dni by 2r, mu 0 dni by 2r. Let me write it more clearly. Mu 0 dni by 2r. Now, if we have to find out the total magnetic field at the center, we need to integrate this, isn't it? So we have to find out B is nothing but integration of dB, that is nothing but integration of mu 0 dni by 2r. Now dn is nothing but this, right? dn can be substituted with where the variable is r, because r we need dr for integration. So we can change dn by this equation and we can write mu 0 I by 2r. dn is nothing but n b minus a into dr. Now see, r and dr, they are the variable, other things can come outside. So we write b equals to mu 0 ni divided by 2 b minus a, it comes out, it is nothing but dr by r. But dr by r, this is a indefinite integral, we have to put the limits. The limit will be what? If we go back, the limit, the r is varying from a to b. The r is varying from a to b, right? Smallest radius a, largest radius b. So it should be a to b. Integration of dr by r is nothing but log r. So it is mu 0 ni to b minus a ln of r, and putting the values of b and a directly you can find mu 0 ni divided by 2 b minus a log to the base e b by a. Let us see which answer it is. Mu 0 ni 2 b minus a log b by a. So this option A is the correct answer. Clear? Next problem. Okay. See this question. An infinitely long conductor PQR is bent to form right angle as shown. So this PQR, the conductor should PQR like this, bend at right angles like this. A current I flows through PQR. Now current I is flowing through PQR. The magnetic field due to this current at the point M, this is the point M, is B1. For this current, the magnetic field is B1. Now another infinitely long straight conductor QS is connected at Q. This is the point Q. So another infinitely long straight conductor is connected at point Q, so that the current is I by 2 in QR as well as in QS. So initially I current was flowing through this. As you have connected another conductor, the current will distribute along these two paths. So this will be I by 2, this will be I by 2. In QR as well as in QS, the current in PQ remaining unchanged, it will be. The magnetic field at M is now B2. So initially the magnetic field was B1, now the magnetic field is B2. The ratio of B1 and B2 we have to find. Okay, moving deep into the problem, first look what is happening. First, this was the current flow marked by the blue line. When current is flowing like this, a magnetic field M is generated. But magnetic field is generated only by the PQ, because QR, as it is oriented along the line, M is lying along the line QR, so this QR part will not generate any magnetic field. So the magnetic field will be generated only by PQ, right? So, the magnetic field B1 is only by PQ, where the current is I. Now, when we have joined another conductor which is carrying I by 2 current with it, again I by 2 is flowing through QR, so QR is not coming into picture. So what is happening? Only PQ was there. Now you are joining another conductor which is carrying I by 2 current. Now the magnetic field, because of this I and I by 2, is B2. So we have to find the ratio. This is the question. Now, so the magnetic field is dependent on the current. Let us see what formula we are using and we can find it. See, magnetic field for a straight conductor is nothing but given by this formula, where suppose we are trying to find out the magnetic field by this straight conductor at a distance of A. If we measure the angles of the end of the coil, this is phi 1 and this is phi 2, then the formula is given by this: B equal to mu 0 I by 4 pi A sine phi 1 plus sine phi 2. Now see, in both of the cases, the coil was like this. First the coil was like this. In this, and this is an infinitely long coil. So for one, phi 1 will be 0, and for other, the phi 1, for this phi 1 is 0, for this the phi 1 is 90 degree. So B for this orientation, B will be nothing but mu 0 I by 4 pi A into sine 0 plus sine 90, that is 1, it is mu 0 I by 4 pi A, right? And that B is nothing but the, if you remember, that is B, sorry, that is B1, that is B1. So this B is nothing but, first it is B1. For B2, we are actually adding another conductor here. For this is B1, right? B2, here the current is I by 2, right? So B2 is nothing but B1 plus B dash. B dash is the magnetic field generated by this current, which is I by 2. Now B1 is this, B dash will be nothing but mu 0 by 4 pi A. Instead of I will write I by 2. So B dash is nothing but B1 by 2. So I can write this B1 plus B1 by 2, that is 3B1 by 2. So we have to find out the ratio between, B1 and B2. So B1 and B2 will be, B1 is B1, B2 is 3 by 2 B1. So B1 by B2 is nothing but 2/3, right? Let us see the answer. So answer C will be our, option C will be our answer. So again, just repeating, we are trying to find out the magnetic field by the coil, the way it is oriented, and we can see the coil, the part of the coil which is lying along the line will not produce any magnetic field. The magnetic field will be produced by the other part, and magnetic field is dependent on the current. How it is dependent, we are seeing by seeing the angle. Like if for any other problem, the angles were something like this, like this is 45 and this is also 45, then also you can find out for infinitely long coil, right, this angle is 90, this angle is also 90. You know all these things, right? So the way we have found, like, the magnetic field is dependent on the current flowing, what are the current that is flowing, and then we have got the ratio. Thank you. We are going into the next problem. Okay. This is an interesting question. Last three questions are from how magnetic fields are generated by the current. Now, this question will see from which part it is. A thin flexible wire of length L is connected to two adjacent fixed points A and B. These are the two fixed points. Carries a current I in the clockwise direction. See, the current is flowing in the clockwise direction as shown in the figure. When system is put in a uniform magnetic field of strength B going into the plane of the paper, the wire takes the shape of a circle. We have to find the tension in the wire. Now, when we have to find the tension, it means what? We have to find the force. The force means now we are coming into the part of where what is the force when a current carrying conductor lying in a magnetic field, right? This is a question. Now see, before moving on to this exact problem, first we have to find, or we have to know why the wire is taking the shape of a circle. What is happening with the wire? Now see, wire is carrying the current in the clockwise direction, right? And the magnetic field is inside. Now, what is the force generated when a current carrying conductor lies in the magnetic field? Is given by B I cross L, right? B I L, right? Yeah. Now, if it is I L L B, no, sorry, this is wrong. I L into B. It will be, sorry. This is I L into B, right? Because I is a scalar quantity, the vector quantities are L and B, right? So force is nothing but the cross product of I, L and B. Now what happens? It is going in the clockwise direction and the magnetic field is like this. The force will be, if you follow this one, or a left hand rule, Fleming's left hand rule, then you can see this is magnetic field B, right? Length is, so the force will be, magnetic field is B in this direction, the length is in this direction, magnetic field B, okay, magnetic field is B, which is going inside, length is in this direction. So the coil is like this, so we can see the length is like this, magnetic field is going inside the board like this, force is outwards. So wherever the length is like this, the force is always in the outward direction. The force generated will always be in the outward direction. If the force is in the outward direction of the coil, it will pull it to form a circle. So finally, when this coil will be like a circle, right, and it is tight, tension will be generated in the coil, so that this tension will actually, the tension that is generated within the coil will actually balance this force whose magnitude is nothing but B I L. Let's try to find out what tension is being generated. Now, after the coil has become circular in shape, let us take a very small region of the coil, which is, say we say it is nothing but DL. sorry. This is the length DL, right? And this is the angle d theta. Now, along this, tangentially, the force will act tangentially at each point, say, and tension will be same. Say this is the tension T, right? Now, what will happen? The force that is acting on the coil because of the magnetic field is outwards, right? This is the force, and that magnitude we know, it is nothing but BIL, right? It is BIL. BIL is nothing but the total length, right? For BIL here it is BIDL because DL is a length, right? Now this force is getting it is getting equivalent to, or the tension, the component of the tension in the downward direction is balancing this force. The tension is acting along the tangent, so the component of the tension will be acting along this line, right? What is the angle here? I'm trying to draw this circle once again. Say this is d theta, right? And these are the tension. This is d theta. If you just, this is another tangent. See, if you draw a perpendicular line, this is d theta. So this will be nothing but, this red will be nothing but d theta by 2. So this will be also d theta by 2, right? This portion is also d theta by 2. Now this is 90. This is 90 as it is tangent. The whole angle is d theta is 90 plus d theta by 2. Now this angle is again 90 because this is tangent. The whole angle was 90 plus d theta by 2. 90 plus d theta by 2. Now this is 90. So this part will be again d theta by 2, isn't it? So let's get back to the original color. So this angle is nothing but d theta by 2. Now if we take one tension T, we have to find out the sine component, because the vertical component of tension T, and there are two tensions in two sides which are balancing this force BIDL. So what is that? The component will be 2T sine of d theta by 2 will be balancing what? B I into DL. DL is nothing but this length, right? Now sine, as d theta is a very small angle, so sine d theta by 2 we can approximate it to d theta by 2, which is equals to BI. Now this DL we can also write in terms of d theta. What is that? DL is nothing but the arc length is nothing but R into d theta. So we can write R into d theta. Now d theta cancels out. This 2 cancels out. So finally we get what? T equals to BIR. Now when tension T equals to BIR, let us see if we can find the answer. Sorry. The answer is not having the R, it is having L, where L is the total length of the conductor. So, what we have found? T we have found B I R. R is not there, R we have taken to be the radius of the coil. Now, the total length is nothing but the circumference. So, L is nothing but 2 pi r. So, replacing r we can write L by 2 pi. So, replacing r we can write T equals to B I L by 2 pi. Is there an answer like this? B I L I B L by 2 pi? It is option C. So, option C, it is nothing but B I L by 2 pi. So, this is the tension that will be generated within the coil when it will be placed in a magnetic field perpendicular to the plane where it is placed, and then the coil will become circular in shape. Let us move on to the next question. Okay. Two particles X and Y having equal charges after being accelerated through the same potential difference enters a region of an uniform magnetic field and describes circular paths of radii r1 and r2. We have to find the ratio of the masses. This question is again one question of movement of charge in a magnetic field. So, first it is given two particles X and Y having equal charges. So, charge, say equal charge is Q, after being accelerated through the same potential difference, let the potential difference is V, enters a region of an uniform magnetic field. Okay, before going into this, first of all, let us find out this, what we can find from this. Having now, when it is accelerated through a potential difference, what will be generated? Its kinetic energy will be generated. So, we can say the kinetic energy of the two particles, let the mass of the two particles, say X and Y, say the mass is m1 and m2 and the velocities v1, v2, but the kinetic energy will be same because they are having they are accelerated through the same potential difference and having same charge, because kinetic energy formula is nothing but half mv square equals to q into capital V, where V is the potential difference. So, we can write half m1 v1 square equals to half m2 v2 square. This much we have understood that how mass and velocities are related for this set of particles. Now, what is happening? They enters a region of a uniform magnetic field and describes circular path. Same thing. The other question that we have done just now was having a current in a magnetic field, now charge in a magnetic field. When a charge is moving through a magnetic field, we know the force that is generated is nothing but BQV. And when the force is again perpendicular to the velocity and the magnetic field, right? And then what happens? The charged particle, it takes a circular shape. It goes through a circular path. When it goes through a circular path, then same, the centripetal force, which is given by m v square by r, is balanced by this force, that is BQV. Right. So, we can find out what is how radius is dependent. The radius r is nothing but mv by BQ. So, the radius of the circular path that the particle follows is given by mv by BQ. See, B is the magnetic field, Q is a charge which are constant. So, R is somewhat proportional to the product of mass into velocity, right? That is the momentum. But we have to find out the ratio of their masses, when the radii are given r1 and r2. So from mass into velocity, there are two variables. We have to change, we have to convert into one, isn't it? So let us see, let us do that. mv by bq, v half mv square equal to qv. We can, from this equation, we can get v square equals to 2 qv by m. So v will be nothing but root over 2 qv by m, right? So v, the variation of b with mass, and this is constant, we have found, right? So we can put this value here, is nothing but m bq. In place of v, we can write right. Now see, whatever we do, don't, when in the time of examination, don't solve much. Try to use your IQ. See, 2 qv, this is constant, it is given. bq, all these are constant, right? So, and there is a root m. This is root m, so we can write r is somewhat one constant k multiplied by root m. So r, the radius, is proportional to the square root of the mass. We have substituted, we have replaced the velocity factor, because radius is proportional to mass into velocity, but we have to bring into mass because we have to find the ratio of the masses, right? So if you square it, so r square is then proportional to mass. So then definitely r square is proportional to mass. So mass, the ratio of the masses x and y, that is m1 and m2, will be nothing but r1 square divided by r2 square. So m1 by m2 will be nothing but r1 square divided by r2 square. Any answer? r1 square divided by r2 square. So answer is C. Circular path of radius r1 and r2. This should have been written in small r1 and small r2, right? Answer is this. Clear? So here we are using basically two equations. One is the kinetic energy equation, half mv square equal to qv. Another is the Lorentz force bqv is equal to the centrifugal force. By getting these two equations, we are finding out the radius, right, in terms of mass and velocity, and we are substituting and getting the answer. Okay. Let us move on to the question. Next problem. Okay, we are already, let us move on to another question of, so this, that was a similar question. As we are running out of time, let us solve one more question of magnetic moment. Because our chapter is, or our topic today is for magnetic effect of current as well as magnetism. So let us see this question. A loop carrying current I lies in the xy plane as shown in the figure. The unit vector k is coming out of the plane of the paper. The magnetic moment of the current loop is. Now, this is a very simple question. Magnetic moment m is nothing but I into the area vector A. I into the area vector A. I into the area vector A. So, here the magnetic moment, it would be definitely this this current is flowing like this. It is enclosing this area, right? So the magnetic moment, and see the direction is this. When the direction is this, right, again we can find out yes, the current is flowing like this. So it is the magnetism is in this, the magnetic field is produced in this direction, which is in the positive direction of the k of the z axis, that is unit vector is k, and we have to find out the area of this loop. See, this in between there is a square of side A. So definitely one is A square, and there are 4 semicircles, means 2 circles, whose radius is A by 2. So pi A by 2 whole square, that is A square plus pi A square by 4, that is, yes, pi, so I can A square pi by 2, yeah, I can write A square pi by 2 plus 1. This is the area. The magnetic moment will be what? Pi by 2 plus 1 A square I k. See, there is one minus k also, we cannot take that. Minus k signifies it is in the inward direction, but we have seen it is in the outward direction, right? So this will be our answer. Okay, our next question. Two particles, each of mass m and q, are attached to the two ends of a light rigid rod of length 2r. So what is said? Two particles of mass m and q, this is also mass m and q, attached to ends of a light rigid rod of length 2r. So this is 2r, so this means this is r and this is r. The rod is rotated at a constant angular speed about a perpendicular axis passing through its center. So this, if is a rod, it is rotating like this, right? The ratio of the magnitude of the magnetic moment, so ratio of the magnetic moment that we have found, like I into A, and its angular momentum, that we have to find out, right? Let this be the angular speed omega, right? So angular speed omega. Now see, when charge is moving, right, what is the current? Current is nothing but charge by time. Charge by time. So here t is nothing but the time period. So 1 by time period is nothing but charge into frequency, right? Here charge is what? 2q. So 2q into, if the angular speed is omega, the frequency is 2q omega by 2 pi is nothing but q omega divided by pi. This is nothing but the current, I. Now see, first we have to find out the magnetic moment. So magnetic moment is I into area, right? I into area, I is what? Q W by pi into area is nothing but pi r square. Pi r square. So pi cancels out. It is q omega r square. This is magnetic moment. And we have to find out its angular momentum. Now angular momentum L is nothing but, angular momentum is nothing but the moment of inertia m r square into omega, m r square into omega, and there are two particles, so 2m r square into omega. So this is nothing but the angular momentum. So, the ratio between magnetic moment M divided by L is nothing but Q omega r square divided by 2 m r square into omega. So, omega omega cancels out, r square cancels out, it is q by 2m. Okay, fine. Our last question for today. Time is up. Just 1 minute, just 1 minute. See, few questions you will also get also into that is on sensitivity, that is statement 1, statement 2. Statement 1 is given, the sensitivity of a moving coil galvanometer is increased by placing a suitable magnetic material as a core inside the coil. It is true, right? Because in a moving coil galvanometer, if you place a soft iron, the sensitivity, that is the B, can increase, the magnetic field can increase, right? And hence its sensitivity can also be increased, because the formula of sensitivity is given by N number of turns, B magnetic field, A area, K is the torsional constant. Now I sensitivity is dependent on B. So if you increase the B, its sensitivity will increase. Now statement 2 is soft iron has a high magnetic permeability, right, and cannot be easily magnetized or demagnetized. Very wrong, very false, right? Soft iron has a high magnetic permeability and hence it can easily be magnetized and demagnetized, isn't it? So this is false, this is true. So you will get this kind of question where reasoning as well as first statement will be the statement and second statement will be the reason. And see, statement 1 is true, statement 2 is true. No, statement 1 is true, statement 2 is true, but statement 2 is not a correct. No, this is also not true. Statement 1 is true, statement 2 is false. So our option will be statement 1 is true, statement 2 is false. So these are the kind of questions that you will get in from this chapter, from this topic, magnetic effects of current and magnetism, right? And prepare well, and we'll come back with a next topic. Happy learning.